This is our centripetal forces and centripetal acceleration first video introduction, and there will be a few examples. Also watch, before you start watching this video, watch the introduction to or the videos for regular physics classroom. They're easier, and you will understand probably more before you jump to these videos, but it's also good to watch this one. So in centripetal forces and centripetal accelerations, if an object, so the centripetal force is not a force like friction or gravity force, the one that we have specific formula for it. Centripetal force can be different types of forces. It can be net force that causes centripetal force, but it does have a formula for centripetal force. So it's not one specific force. So let's say force of gravity can be centripetal force for the satellite, or when the car is making a turn on the curb, the car is having friction force that is centripetal force, because without the friction the car would not be able to make the turn. And so what's interesting is when the car is making the turn, let's say here is the car, the wheels and the car itself. The car is moving forward, so the velocity is gonna be forward, but the friction is gonna be inward, and that friction, the one that is inward, is actually the friction force, and it is your centripetal force, which has its own formula. So in this case, the friction force becomes centripetal force. That's without bank curve, like with on the flat surface. And acceleration also, so if you see centripetal force formula, it is still ma, but in this case it's mac. So centripetal force, it's always going to be toward the center of the circle. So if this is the center of this circle, then the centripetal force is always going to be toward the center and perpendicular to the velocity, and centripetal acceleration is also toward the center. So you could have linear acceleration, where speeding up, moving faster and faster, your velocity is increasing. So you would have linear acceleration, or they call it tangential acceleration. But if you're moving at the constant speed, so if your velocity is not, if your speed is not changing, your speedometer is showing certain number without changing, so you're moving at the constant speed, your velocity is still changing, because velocity is speed, which is the magnitude of the velocity, and the direction. And if your car was maybe in this position, then your velocity was in that direction. Velocity is always perpendicular to the centripetal force, and centripetal acceleration is also toward the center. Centripetal acceleration is always toward the center. And centripetal acceleration has a formula on its own as well. So it's not the change of the velocity over the time. It is velocity squared over the radius of curvature of the curve that is object is moving. So you can also have a tension, like on the picture on the right on the top. You can see that there is a ball moving in a circular path. So there is a circular path, and in this case the tension force becomes centripetal force, and you see that centripetal force and centripetal acceleration toward the center, and the velocity is perpendicular to acceleration and to the force. So this is what you need to know to start with, and now we're going to look at the examples. Examples in AP Physics will start a little bit not difficult, but they are more challenging than regular physics. So if you look at the regular physics videos in the description, you will have a better understanding of these, especially if you struggled in the classroom or have been struggling. Then watch those and then come back to this video. So here is the first example we're going to be looking at. A car travels at a constant speed of 30 miles per hour. Let's convert 30 miles per hour into meters per second. So 1 mile is 1.6 kilometers, or 1600 meters. So if you have 30 miles per hour, that's the same as 30. And instead of the miles, I'm gonna write meters, which is 1600 meters. And instead of the hour, I'm gonna write 3600 seconds. Then to simplify this, I can divide by 100 and by 100, and I can divide by 3 and by 3. So I get 160 in my numerator, and I get 12 in the denominator, and it's still meters per second. I can divide by 4 and by 4, so I get 40 over 3, which is 13.4 meters per second. So a car traveling at a constant speed of 30 miles per hour, which is 13.4 meters per second, on a level circular turn of radius 50 meters. So I know the speed of the car, and I know the radius, as shown in the bird eye view in the figure. What minimum coefficient of static friction between the tires and the roadway will allow the car to make the circular turn without sliding? And I wanted to pay attention here that it is a static friction because the car is not skidding on the road. It is traveling without sliding. So it is static friction. So I will say that the force of friction in this case, let's call it little f. The force of friction is going to be our little f, is your centripetal force. So here I see the force of friction toward the center. And so if this is the force of friction toward the center, you have the normal force acting on the car, and you have the force of gravity. Because the car is not accelerating up and down, your force of gravity is equal to the normal force. So for the friction force, I can say that is mu, and it's static, times n, which is mg, and equal to centripetal force, which is mac. That is the same as mv squared over r. So if I look at this part is equal to that part, and I can divide both sides by m. So if I plug in my numbers, I will get that mu is equal to v squared over rg, and that will give me 13.4 squared divided by 500, and equals to 0.36. So your coefficient of friction has to be equal to at least 0.36 for the car not to slide or not to skid on the ground and stay on the track. Let's look at this example. If a car negotiates the 31-degree banked curve, banked means it's not the flat surface curve but has an angle as shown in the picture, with a maximum radius of 365 meters, too slowly, it tends to slip down the incline of the turn, whereas if it is going too fast, it may begin to slide up the incline. Find the necessary centripetal acceleration on this banked curve so the car won't slip down or slide up the incline. So the forces we see acting on the car are the force of gravity, mg, and the normal force. And if we don't want the car to slip down or slide up the incline, let's say if it is gonna slide, so if it moves too slow, then it wants to slide down, so the friction force is going to be up. So I'm going to call this force friction force. So I have the friction force, mg, and normal force. And it has acceleration toward the center. So let's say this will be our centripetal acceleration. And as before, I want to choose the direction of my forces, x and y, or my axis, aligned with the acceleration. So in this case, I'm not going to turn like we did in forces and dynamics when we did incline. I'm not going to turn my my x and y's. I'm going to keep them as they are. So here is my y and here is my x, and x is aligned with acceleration. So the forces that are not aligned with acceleration, my x and y, are the friction force. So I need to make the horizontal component and vertical component of friction force. This angle is the same angle as theta angle, and I need to make my normal force as horizontal and vertical, and they give you that this angle is theta and this angle is theta. Let me prove it to you so you understand where it comes from. So if I have this big triangle and here is theta, then I'm gonna make this here, this is right perpendicular angle, and this is the normal force. The normal force is always perpendicular to the surface. So from here I can see that this angle is 90 minus theta, then this angle is theta. So if this angle is theta, then that angle is theta, because it has these two lines crossing, the blue one and the green one, and these are the internal angles, or vertical angles as they're called. So they're equal to each other. So that that angle right here is also theta. So from this information that I know, I have my horizontal forces, which is F cosine, the friction horizontal component, and I have the normal sine, and I have vertical, which is normal cosine and friction sine. So now we're going to use an acceleration in this direction. Now we're going to look at the Newton's second law, F net is equal to ma. So for the horizontal forces, I'm going to choose positive direction of the acceleration. So for the normal force, horizontal blue one, I have positive n sine theta. Then I have minus, the other second one is negative because it's away from the direction of the acceleration. And let's call it centripetal acceleration. So the other one is negative. So that one is F cosine. So these two forces, there's no other horizontal forces acting on the object or on the car. And that is equal to mass times acceleration. So the mass of the car and centripetal acceleration. For the vertical forces, I have two green ones up. So I have n cosine up, and I have friction sine up, and I have minus mg, but I'm going to move it to the other side, to the right side, and equals to 0 because there is no vertical acceleration. So it would be minus mg, but I'm going to move it to the right side, and I have equals to mg. So I have these forces so far. I'm going to replace my friction force with mu times n. So what I have on the left side for the top equation, I have n sine theta minus mu times n cosine theta, and equals to mac. And for the bottom equation, I have n cosine theta minus mu times n sine theta, and equals to mg. I showed you this trick in the past, so I'm gonna factor out n. So let's take n out from both terms. So n will disappear from over here. And I'm gonna take the same n out from the second term, the second equation. And n will disappear from over here because I took n out from those two terms. And then I'm going to use this little trick. I'm going to divide the left and right sides of the equations by each other. Then n and n cancels, and m cancels. And what I have left is They ask me to find the necessary centripetal acceleration. So after I cancel m's and n's, I have this. I can move g to the other side, or times both sides by g. Then I have centripetal acceleration is equal to this whole expression. And then I can plug in my numbers. For A, they tell you neglect the friction, so we don't have to use this term that has mu, coefficient of friction. If you have a problem when they say don't ignore the friction, then this is the formula that you would have to derive and use. But because we don't have friction, or we say it's frictionless surface and the car stays on track only due to the incline, then my centripetal acceleration is equal to g sine theta over cosine theta, or tangent theta, the same as g tangent theta, and centripetal acceleration is equal to 5.8. So I have 5.8 meters per second squared. That is if I plug in g as 9.8, and if I plug in 10, then I get 6. And then they ask you calculate the speed of the car on this during this race. Then I have centripetal acceleration is equal to v squared over r, and I need to solve for v, so v is equal to the square root of ac times r. So v is equal to AC is 5.8, and the radius is 316. So that will give me 42.8 meters per second. So the car is moving at this velocity and is not sliding down. So this is the minimum velocity the car needs not to slide down. So this problem was without the friction. You can have the same question with the friction, and this is when you use this equation with mu, or the one that we derived, this equation, with coefficient of friction. But ours was without the friction, so we didn't have to plug in the coefficient of friction. And never memorize the formulas, because something will change in the problem and you will not know how to solve. So you always want to make sure that you know how to derive these formulas. A lot of AP exam questions require you to derive the formulas. So you learn to derive the formulas in engineering and further studies that you will have at the university. You always want to know how to derive the formulas. Here's one more question I want to look with you at. A roller coaster car moving around in circular loop of radius given 10 meters. What speed must the car have on the top so that it will just make over the top without any assistance from the truck? That means that the cart on the top has to have normal force is equal to 0 acting on it. And then what speed will the car have at the bottom of the loop? And what will be the force on the passenger at the bottom of the loop? So here I'm going to draw the loop so I can explain to you how the forces are acting. So if the cart is on the bottom, the forces acting on the cart are the normal force, or the force of gravity, the normal force, and it also has centripetal acceleration toward the center. And in this case, your normal force is your centripetal force, because without the normal force, the car would not be able to make the turns. So for the net force at the bottom, I can write that normal force is positive, mg is negative, and acceleration is up, it's positive, so that's mac. So the normal force at the bottom is mg plus mac. So normal force is usually like your weight force, like if you're standing on the scale, and the normal force would show you how much you weight. But because there is acceleration, and in this case centripetal acceleration, the weight is going to show more when you're at the bottom of the loop. Now, if you were on the top of the loop, let's choose a different color. So if you're on the top of the loop, so here is the car, the force is acting on you, mg, the normal force, but they say this normal force is 0 because the car barely makes it through the top without the assistance of the truck. So in this case, the normal force is going to be equal to 0. And then you have centripetal acceleration, which is toward the center. So at the top, you have negative normal force for net is equal, F net is equal to ma minus mg and equals to negative mac because all of them are pointing down. So your normal force in this case is equal to mac minus mg. So your normal force in this case is lighter, not equals to mg. It's less than mg because it's the difference between these two. So here on the top, it's going to be the difference between these two. And at the bottom is going to be the sum of mg and mac. And they ask you the speed must the curve have at the top of the loop, so it barely makes it through. So because the normal force is equal to 0 in this case, just in this case, doesn't mean always will be equal to 0, then your mac is equal to mg. The mass and the mass cancels, so your ac is equal to g, and that is v squared over r is equal to g, and the velocity in this case is equal to the square root of rg. And then we have velocity is equal to, if I plug in the numbers for the radius 10 and g is 10, I get 10 meters per second. So this is the minimum velocity needed for the car to stay on the track, not fall down, but still not exert any normal force on the track on the top. And then for the bottom one, speed will car have at the bottom of the loop. So now I have to do the same for the bottom of the loop. So for the bottom of the loop, it's a little bit tricky. So what happens on the top is that you have potential energy at the top, which is mg and h equals to mgh. And you have kinetic energy at the top, which is 1/2 mv squared. And the velocity is 10 meters per second, or I can say that the velocity is equal to g in this case. I will tell you why g, because in this question, when they give you answers, it was a multiple choice question. The answer is written very tricky, so it's just for now because it's equal to 10. So you could say it's equal to 10, but I'm going to write it as g. So at the bottom, your kinetic energy is going to be turned into the potential energy. So at the bottom, you have all this energy converted into kinetic energy. So at the bottom, I have kinetic energy of 1/2 mv, and I'm going to call it the bottom squared, is equal to potential energy, which is mg, and 2 times the radius, because that's the height, and plus 1/2 m and v top squared. And this is your v top, the one that we just found, the velocity at the top. So, and instead of saying v top squared, I'm gonna plug in g, because that's how they solve it. So vg squared, because top velocity, not always, just in this case, because we got top velocity is equal to g. So I'm gonna times them all by 2. So times by 2, times by 2, times by 2, and I get, and cancel all the m's. I have v bottom squared is equal to 4, this one is 4rg plus g squared. So if I times them all by 2, the last term has no fraction. And because r is also 10, so what they did in the book, they wrote as 4g squared plus g squared, which is 5g squared. So v at the bottom is equal to the square root of 5g squared, which is g square roots of 5 meters per second. A little tricky how they did it, but they wanted you to recognize that you got velocity equals to the amount what g would be equal to, and plug it in to solve this question. And then for C part, they ask you what will be the force on passenger at the bottom of the loop. So the force at the bottom of the loop, which is the normal force, is equal to mg plus mac. So we have the normal force is equal to mg plus the mass, and vb squared is equal to 5g squared. So that is 5g squared, and that's vb squared, which is v squared over r, which is 10. So the normal force is equal to mg, then I have plus and m, then I have 5g, and r is 10, so that's like 5rg squared, and then r is 10, so that's the same as g, so I can cancel one of the g's, and that will give you 6mg. So it will be 6 times its normal weight at the bottom. In other words, the car at the bottom will experience 6 times more weight as if it was not moving in a circular motion. Like if it was standing, it would weigh so much, but at the bottom of the circle, moving in circular motion, it will feel 6 times more force acting on the passenger and on the car than it would be normally without the circular motion. It's actually vertical circular motion. Horizontal circular motion doesn't have these little tricks. I will stop here because I don't have enough time to fit another question into this video. I only have 3 minutes left. And so this was our introduction to centripetal forces and acceleration. And I think there will be at least 2-3 more videos related to this lesson for AP Physics 1 in our classroom. And you can always email me if you find something online or in the book that you don't understand and cannot solve, and I can make you another video explanation related to that problem. Thank you, and see you in the next video.